Welcome everybody once more to the official IAU conference series. As usual, this is about massive star, and today is a very special day for me because I'm going to introduce someone who has been my big brother and also some of my most important reference since I started my piece in 2000. This is Miguel Urbaneja. So welcome, Miguel.
Thank you.
Miguel is presently scientific staff at the Universität Innsbruck in Austria. He did his PhD at the Universidad de La Laguna and the Instituto Astrofísica Canarias in Spain under the supervision of Artemio Herrero. The title of his PhD, which he defended in 2004, was Be Supergiants in the Milky Way and Nearby Galaxies, Models and Quantitative Spectroscopy. This topic has been at the core of his research interest since then, where he has been nicely combining an amazing long-term observational approach with a parallel development of techniques to perform quantitative spectroscopic analysis of this type of stars. And this includes some work with stellar atmosphere codes and atomic data, as well as evaluation of the utility of the use of advanced computational techniques, including Bayesian approaches and machine learning, to improve the reliability of the outcome of this analysis. After finishing his PhD thesis, he moved to Hawaii to join the group of stellar astrophysics led by Rod Kudrycki, where he stayed for almost 10 years. And after that, in 2013, he moved to Austria to join the group of researchers with interest on massive stars, which Norbert Prisvilla was starting to build. I'm sure Miguel is going to showcase much better than me the variety of topics covering several aspects of modern astrophysics, which can be investigated using the spectra of blue supergiants. I'm going to stop here with the introduction. However, before giving you the floor, Miguel, I want to warmly thank you once more for accepting the invitation of the IAU G2 Commission to tell us about your research. So I hope you all enjoy this seminar whenever you want. Al ataque.
Thank you, Sergio, for the kind words. Thank you very much for dedicating time of your day to listen to this presentation. And also I would like to thank the Commission for inviting me. So before we move with the science, along the invitation came a soft request to introduce a bit the institution. So we will move to that. So as Sergio said, I am a scientific staff of the Institute for Astro and Particle Physics of the University of Innsbruck. The institute is, we have something like 40 people working here between faculty and support. And the institute is organized in different research groups, covering topics from extragalactic astrophysics to astroparticle physics, and numerical simulations, and so on and so forth. So you have here the webpage of the institute with the different groups. Each group is led by one of the professors. And the names of the groups are a bit misleading because, as you can see, for example, we have a group on stellar evolution astrocosmology, another group on stellar astrophysics, and another group on galactic astrophysics, that sometimes the topics are interconnected between different groups. So my group, or the group I am a part of, is Galactic Astrophysics. It's led by Norbert Prisvilla, and basically everything related to massive star research is done in this group. There is also a part of, so a group of people in this group that are dedicated to the development of pipelines for the instrumentation of the ESO extremely large telescope. This is part of the agreement that Austria has with ESO. So if you have questions or an interest to visit or anything like that, please contact any of the group leaders, and then they will direct you to anything or answer your questions. So moving into the science, the idea of my idea when preparing the talk today is that at the end of the presentation, you get the impression that massive stars, in particular blue supergiants, can be used as tools to investigate the nearby universe. they are very interesting objects, and studying their physics is actually very important, but they can also be used to investigate the nearby universe. And then the primary question is how far can we go with individual objects? Well, the answer is that the brightest stars remains observable. Here on this image, you have part of the disk of a galaxy at 2 megaparsecs, so well beyond the limits of the local group. And those things that are marked with the red circles are candidates, blue supergiants, for follow-up spectroscopy. The reason why blue supergiants are preferred or useful for this thing is that they are intrinsically very bright targets. Within the local group, within 1 megaparsec, one can do easily high-resolution spectroscopy or intermediate resolution spectroscopy with current instrumentation because they are very bright. When you want to move beyond the limits of the local group, you need to sacrifice resolution because, as we will see in a minute or in 2 minutes, signal-to-noise is a critical component. So one has to sacrifice spectral resolution, but still, it is possible to get high-quality optical spectra for these objects by using the highly efficient multi-object spectrographs that are attached to 10-meter class telescopes, like, for example, LRIS at Keck in Hawaii or FORCE 2 at the VLT in Chile. Another important aspect of blue supergiants, or B and A type supergiants, is that the optical spectra are very rich in metal lines. So they contain a big amount of information that we can exploit. To give you a sense of what this means, here you have a representation of what is called the local volume. So this is centered in the Milky Way and is a cube of 16 by 16 by 16 megaparsecs, so a radius of 8 megaparsecs around the Milky Way. Each single dot in this figure is a galaxy. And the gray circle depicts the limits of the local group. So the Milky Way and M31 groups, all your favorite stars are within that circle. With blue supergiants, we can comfortably reach up to 7-8 megaparsecs. And this is depicted by this blue circle. So as you can see, now you have many more galaxies, many more environments where to study massive stars, where to study blue supergiants. The way we go about finding these objects is actually not complicated at all. Blue supergiants are very bright and they look blue. So in a color magnitude diagram, they will be in this selection box. Okay? So these are our candidates for follow-up spectroscopy. And then what we do is in the same high spatial resolution images obtained with HST that we use to compute the photometry, we can look at how they look. We can, for example, study the PSF and select the best candidates that we think they are resolved for follow-up spectroscopy. This is an example of stars in the galaxy, and you see 3621. This is a galaxy that is about 7 megaparsecs away from Earth. And you can see how bright these targets are and how they dominate basically anything around. So it's not, I mean, it's challenging, but it's possible to collect very high quality optical spectra of these objects. So, as I said, blue supergiants have a very rich spectra. Here you have a sequence from a hot B0 at the bottom to a tepid A3 on the top, and you can see many spectral lines there, not only hydrogen and helium, but also lines from many different species. So there is a wealth of information that one can exploit from this spectra. Of course, these are part of the optical spectrum of galactic stars observed with an intermediate spectrograph. When you move away from the local group, as I said, one has to sacrifice resolution. So the spectra will look like something like that, which in principle looks scary, but there is a lot of information there that we can extract from these things, okay? And I will try to show you how we do that. Now, the basic tool, well, the basic observation that we get is photons from the star. and we need to translate those photons into physical parameters. Okay, and the way to do that is something called quantitative spectroscopy. Two basic ingredients are necessary for quantitative spectroscopy. First, you need to have numerical simulations of the stellar atmosphere that will allow you to say, okay, these are the parameters characterizing the object. This is how the object should look like. Okay, this is what we call normally model atmospheres, stellar model atmospheres. The second component is the inference process, because your simulator, which is a forward simulator, what does is, given a set of parameters, you get how the star look like. But what you want is exactly the inverse process. You get an observation, and you need to infer what parameters would describe that star best. Something that I want to emphasize, this is not just line fitting. Okay? We are using physically constrained models. So this is more than line fitting. The other point, or a point that is important for this, is that stellar spectrum is actually a fingerprint of the atmosphere of the star. In a classic way, we tend to think that there are indicators that are quasi-separable or separate indicators that will tell you something about the properties of the star. For example, for the effective temperature, the classic approach is to compare lines from different ionization stages, and this will tell you something about the effective temperature of the star. In the case of massive stars, hydrogen lines are very sensitive to the Stark effect, so they are sensitive to the density and hence to the gravity of the star. In the case of elemental abundances, you can use the strength of metal lines. But the important thing to remember, or something very important to remember, is that in reality, every single wavelength in the spectrum, every single point, contains information about the atmosphere of the star, about the temperature, the density, the velocity fields, the composition. Not every point will give you the same amount of information. Not every point will give you the same information. Some wavelengths will be more sensitive to one parameter, some others will be to another, some will not be sensitive at all, but there is a lot of information in the spectrum. Also, not every point is independent. There are covariances between the points, and this is very important. Now, from the practical point of view, we divide the stars into groups. We call OB stars to anything that is cooler than O9 and hotter than a B4, for example. And we call BA stars to anything that is in between B8 and A3 and A5. The reason is just practicality. As you can see in the spectrum of the OBs, the critical indicators, like for example the silicon triplet here or here, and the silicon 4 line here or here on the silicon 2, are still accessible, plus the hydrogen and helium lines. So classic approaches can be used to analyze this spectrum. In the case of the BA supergiants, the hydrogen lines are still available. In some cases, like for example in this B8, the helium lines are still available. The problem comes, or the trouble arises, from the effective temperature indicators. In these cases, we need to have access to weak lines from neutral species, like magnesium 1 or iron 1. At these resolutions, it's impossible to get them. So one has to find another way to derive the effective temperature for these objects, and I will discuss that in a minute. We model each group with different codes for reasons that now I don't have time to explain. It will take long. But what is important for me to say now is that in the region where the codes, the region where we can apply both codes simultaneously, the solutions are consistent. There is no breakup in there. We would derive exactly, within the tolerance, we will derive the same parameters. In the case of OB stars, we work with FastWind, which is a non-LTE unified model atmosphere. In the case of the BA stars, we use the technique developed by Pritzvila et al. 2006, which is a hybrid approach in which we use LTE atmospheres, and on top of that, we run non-LTE for the populations and the emergent spectrum. Something that is very important, is that modern codes are fantastic. They provide you the framework in which the physics is solved. You have your physics described by a number of equations that describe the physical processes, and you have the algorithms that will solve those equations. But it's a fundamental ingredient that has to come there, and is atomic data. And non-LTE codes are machines that require tons and tons and tons of atomic data to describe the interaction between the radiation field and the matter. So the predictions of your code are not only or are also dependent on the atomic data that you are using. Two people can use exactly the same code, but if the atomic data is different, you will have different predictions. Whether this is relevant or not, it will depend. So one thing that we do is that as much as we can, we use the same atomic data in both cases. So FastWind, our use of FastWind and our use of ADS, we always try to homogenize the atomic data, but it's used by both codes. Right, so then comes the point of codes and models are awesome, but they are still not true. They are not nature. So there are limitations. And it's extremely important to understand the limitations of your modeling. It doesn't matter what code you are using, every single code will have limits. It's designed to do things, and it should not be used out of the regime where those codes are designed for, the same for the atomic data. So the first step, or the zero step in the whole process, is to analyze and test your modeling where the amount of information is maximum. So with high quality, high resolution, very high signal to noise, spectra of benchmark stars that you think that you understand, and you see and test your model atoms, your model atmospheres, and so on and so forth. The trust that you have in the low resolution stuff is built upon this foundation rock. So if this point is missing, if the testing of the models is missing, anything that you predict and you say afterwards is on a wobbly surface. Of course, when you move from high resolution to low resolution, no matter how high the signal to noise is, there is a loss of information. So for example, at low resolution, you will have blending of features. One of the important aspects is that you lose information from weak lines, and this immediately goes into the fact that you lose sensitivity to an important parameter when you are deriving abundances, which is microturbulence. Which this means, not only microturbulence in general, is that the posterior distribution of your parameters will widen. So the uncertainties will be bigger, and you might have larger or increased degeneracies between your parameters. But still, you can develop, and we have developed mitigation strategies to try to minimize this effect. So for example, you do simultaneous fitting of wide ranges in the spectrum, because again, and this is the important theme, each wavelength point in the spectrum carries information, some more, some less, but you can exploit that. The other thing that you can do is to use hierarchical priors. So for example, in the case of BA supergiants, what we do is to put a prior on the microturbulence based on what we have derived or has been derived on the analysis of high resolution data. Of course, there is information that you completely lose. Like for example, you cannot say anything about rotation, or you cannot say anything about microturbulence, because the broadening of your observation is dominated by the instrumental profile. So you lose information. Nevertheless, when you have a wide range observed, there is a significant amount of information that you can recover from low resolution. A critical aspect is the signal to noise. I mean, because when you look at these spectra that are in the background, you can see that you will need to have a very good signal to noise to be able to define the continuum and also to measure your lines. So what we did is a large number of simulations in which we injected noise into simulated spectra and then put those spectra through our analysis machinery and compare what recovered in terms of metallicity with respect to what it was introduced. And this was done for many simulations, and several times, I mean, something like 200 times the same amount of signal to noise, and so on and so forth. So this is summarized in these figures, where you have in the x-axis the signal to noise ratio, and the y-axis you have the difference between the input metallicity and what you recover. For solar metallicity, basically you can see that even down to 30, you can have reasonable results. We said 50 would be our limit. When obviously, of course, this depends on the metallicity. When you go to when you go to lower metallicities, the effect or the loss of information is more significant. Still, the about 50, with a signal to noise of 50, you can recover with a reasonable uncertainty the metallicity of the object. This doesn't only depends on the signal to noise, this also depends on the spectral type. B8, a B8 star will, for a given metallicity, will have weaker lines than an A2. So it's easier to derive metallicities for the same signal to noise from an A2 than from a B8. So all these things come into play when you are designing your observations, for example. Right, so one of the things that I mentioned is that at low resolution for the B8 type stars, you lose the effective temperature indicator. So what we came out with is using the Balmer jump and this index that we call dB, which is just a relative measurement between the flags after jump, after the Balmer break, and the flags before the Balmer jump. And you can see in this figure, in a Teflon G plane, isocontours of this dB index in our grid of models, and they behave very smooth, very nicely. If you would overplot here the isocontours of the equivalent width of hydrogen lines, for example, this would go not orthogonal, but they will cross like this. So using the Balmer lines and the dB will allow you to find a unique solution in the plane Tef log G. As an example, this is the galactic supergiant Deneb. What you have in the main plot in here is the final solution, and the dots are photometric measurements in different bands, optical bands and infrared bands, and then you have the IAU spectrum here. In the insets, you have a variation of the effective temperature of minus 5% and plus 5%. So the dB, the Balmer jump, is very sensitive to variations in the temperature. There are two things that I want to mention here. One is that even though the region where the dB index is measured is small, still it is very important to simultaneously derive the temperature and the reddening of the object. This is why it's so important to have a long spectral energy distribution baseline. Changes in there because of the extinction law will move the temperature that you are deriving. So this is one thing that one needs to take into account. The second thing to take into account is the extinction in the observatory. It's not the same to observe in Chile that to observe in La Palma, and the atmospheric extinction needs to be taken into account. And the third point is slit losses. One has to have a very good understanding and a very good model to correct for possible slit losses during the observations. Otherwise, the dB that you are measuring is not the real thing. So when you account into all these things, still the question, is there any systematic effect? Is the dB temperature or the Balmer-Jan temperature are consistent with what you would derive by a classic ionization equilibrium analysis? We did that. We did this kind of a study using a large sample of B and A supergiants in the Large Magellanic Cloud. The reason to use the Large Magellanic Cloud is that it is easy, or you can get relatively high resolution observations with very high quality for this kind of calibrations. You need an instrument, of course, that will go down to the Balmer-Jan. In this case, this was MAGE at Magellan. And what you have in the upper panel, this panel, is a comparison. In the x-axis, you have the temperature, effective temperature that would derive from a classic ionization equilibrium, either iron 1, iron 2, or magnesium 1, magnesium 2. And in the y-axis, you have the temperature that you would get from the Balmer-Jan. And as you can see, there is no systematic effect. They are actually within the uncertainties of both analyses. They are exactly the same. In the next panel, this one, in the x-axis, we are representing the quantity that we call the flux-weighted gravity. This is a proxy for the luminosity. In fact, I give you there an expression in which you can connect the flux-weighted gravity to the spectroscopic luminosity. So this is a measurement of, or a proxy for luminosity. The lower the value, the higher the luminosity of the star. Okay. So as you can see in that plot, there is also no, in the range that we have studied, I want to say that, there is no dependence or there no systematic effect in the determination of the temperatures with luminosity. Okay. So this can be trusted, or I mean, this shows that both things are consistent, and then the analysis can be trusted. Besides doing all of this, we were fortunate enough to, in some cases, have observations of the same stars, both with low resolution data and high resolution data. I'm showing here one of these examples. This is a star in the galaxy WLM, so sub-SNC metallicity galaxy. What you have in this panel is the first two data analyzed. This is what I'm showing in blue is the final model coming from the analysis of the star. You have the long spectral energy distribution, including photometry from our own Araucaria project and photometry from the local group Survey of Galaxies by Massey. And of course, you have the Balmer-Jan variant that is well reproduced. And in the lower panel, what you have here is this star was studied years before us by Kim Ben and collaborators. And they use UVES, high-resolution spectrograph. So actually, the spectrum is 32,000. And what I am showing in that plot is the model that was calculated for the solution of force degraded to the resolution of UVES on top of the UVES spectrum. And this is one of the things that is very convincing. So, and this is not the only star for which we have done that. So one can trust the results that are coming from the low resolution, high quality, low resolution spectrum. Okay. Of course, it has limitations, as I said, but one can trust these things. Now, before we move, I want to again make this point. One has to understand what are the limitations of the modeling. One has to understand what are the limitations of the observations. We are pushing the supergiants to the limit of observability of what is useful for them. Things that make these objects very useful, very interesting, like the extreme luminosities, or that the spectrum is rich, full of metal lines. These things are both a blessing and a curse, because now you need to model atmospheres that are quite complex, and you have to be able to extract information from blended data. So it's not easy, it's not impossible, it's very important that you understand the limitations in everything that you are doing. Right, so at this point is when we move from, okay, we can extract information from the spectra, let's use these things to study the universe. So we can do stellar physics studies, of course, but I am focusing today more on what we learn about, or showing you what we learn about their host galaxies, how far they are, and how can we measure even the current expansion rate of the universe from the using atmospheres of blue supergiants. This is an example of 3 objects, one in the LMC, one in WLM, and one in Leo A, to show you that when you lose resolution, but you apply what I said before, you still recover information and to a very good level. So all of these objects are in galaxies that are sub-solar metallicities. In fact, Leo A is the galaxy with the lowest metallicity content that we have studied so far. And you can see that the models that are calculated for the outcome of the analysis process very much predict what we observe in the spectrum. One thing that you can do is, if you study many stars in a galaxy, in this case in a spiral galaxy, is to see how the metallicity, the metal content of the atmospheres of the blue supergiants, changes with the location with respect to the center of the galaxy. This is what is called gradients. Spiral galaxies always sustain a metallicity gradient, and this is related to the formation and the evolution of the galaxy. In this case, is NGC 300. NGC 300 is a twin of M33, so a small disk galaxy, but is at about 2 megaparsecs away. In this plot, I am showing in this golden color, these are the blue supergiants that were analyzed in Kudrytski et al. 2008. In pinkish, you have metallicity measurements from ionized gas, from H2 regions, using a particular technique, the determination of the electron temperature of the gas. And in blue, you have metallicity determinations from low-resolution J-band spectra of red supergiants done by Gazak and collaborators. What is important for me here is to stress that these are 3 very different kind of astronomical objects. They are analyzed in very different ways. The observations are very different. The physical models that are used to interpret them, they are very different. So the systematics are very different. Nevertheless, the 3 experiments are telling you the same thing. And this is very reassuring, because no one believes that stars are the atmosphere of a star, either plane parallels or a simple sphere. Stars are very dynamic objects, and we have limitations in modeling them. But when you see something like that, where the systematics are completely different, and still they are giving you the same result, then we are doing our level of confidence increases. Besides doing this kind of studies in galaxy to galaxy, you can combine all the information for many galaxies, and you can create something that is called the mass metallicity relationship of star-forming galaxies. This is very important because this is basically is one of the fundamental scaling relationships of galaxy formation and evolution. So I'm showing you here our mass metallicity relationship for star-forming galaxies in the nearby universe. In the x-axis, you have the baryonic mass of the galaxy. In the y-axis, you have the metallicity now derived from individual stars. So in each galaxy, we have a group of blue supergiants analyzed, and this is what is going there. For full disclosure, because as I said, the spirals sustain a gradient, the standard notation in this case is to choose a point in the disk of the spiral galaxy and quote that abundance. Okay, so this is where you have single point for M31 or the Milky Way and so on and so forth. So you can see how, and this is explained again by formation and evolution of galaxies, how more massive galaxies are more metal rich. They evolve faster. They use their gas content faster in producing stars. And in this relationship, we are covering from basically M31, which is the most massive and more metal rich that we have observed so far, to Leo A, which is the smallest dwarf and less metal that we have observed so far. Now, for the last part, and I don't know if I'm going too fast, for the last part, I want to discuss distances and cosmology very briefly. And it's the fact that from the same atmosphere where you get information, if you combine your spectroscopy with photometry, you can derive star by star the reddening. And this will allow you to, using something called the flux-weighted gravity luminosity relationship, measure distances between galaxies. The FGLR, for short, was introduced in 2003 by Kudrycki, Bresolin, and Pritzbiller. And this is a pure empirical relationship. Sometimes I think there is some confusion because in the original paper and some other papers, this relationship has been tried to be put on the grounds of evolutionary models. Evolutionary models do not enter here at all in these calculations. They support the existence of this relationship, but they don't enter in our FGLR. Okay, so this is a pure empirical relationship between what we call the flux-weighted gravity, which is this quantity, and the luminosity of the object. What you have in this figure is actually the FGLR for 110 stars in 6 different galaxies. Okay, and remember the highest luminosity is here. So very clearly you observe a relation there. To create this figure, what we did was to use the distances to the galaxies obtained by other methods. But what we want is to use this relationship to measure our independent distances. So the way to do that is that you choose an object, in this case the Large Magellanic Cloud. You use that as your calibrator. By comparing the distance of the FGLR of any other galaxy to the LMC, you can get the distance between the galaxies. The reason to get the Large Magellanic Cloud, there are several reasons. First of all, as I mentioned before, it's easy to collect high quality, high resolution data of blue supergiants in this galaxy. The second reason is that the LMC plays a fundamental role, a key role in the construction of the extragalactic distance scale, which is something that is necessary to determine the current expansion rate of the universe. Now, we are very close to the airport, I'm sorry. Someone is taking off. So that's the second reason. And the third reason is that, why the LMC is so important also, is because the distance to the Large Magellanic Cloud is known with a very high precision thanks to detached eclipsing binaries. Okay, this is a geometrical measurement of the distance, and it's extremely well known. This is work that was done years ago by Gregor Pietrzyński and collaborators. So these are the 3 reasons to choose the LMC. So once you have your calibrator, comparing the distance, also comparing the FGLR will give you the relative distances between both galaxies. So we have applied that to many galaxies and compared the distances that we get from the FGLR with the distances that you would get from other classic methods, and you get quite good consistency. And one of the things that we have done recently is apply that to M101. M101 is a beautiful galaxy that is at about 7-8 megaparsecs. The important thing is that this is one of the closest galaxies in which a supernova 1A happened. So we can use that, our distance to M101, to calibrate the magnitude of the supernova and then to get a measurement of the expansion rate of the universe. And we did that, and the value that we got is this one, 70. So from the massive stars, 72.5 plus minus 4.6. You can compare that with what is called the consensus value, which is this one for the local universe. And you can see that, of course, we have a larger error because we are considering only one galaxy. But what is important is not the amount of the error at the moment. What is important is that we have a completely independent systematic budget here. We are using completely different things. We are doing a spectroscopy of massive stars. We are not doing photometry of Cepheids or photometry of the tip of the red giant branch or anything like that. Yet, we have a result that is fully consistent with what is being derived from all these other methods. And just to give you an impression, I use this on my lectures of the extragalactic distance scale. You have different kinds of measurements of the expansion rate of the universe in the local universe, so the nearby, so ranging from CFITs to so AGB, oxygen-rich star, the MIRAS, to, for example, gravitational lensing, or the movement, the geometrical movement of water masses around black holes in the center of the galaxies. So all of them provide a very consistent picture that locally, or what we measure locally, is what is called high value, 73, while every single, or all the measurements that come from the early universe, so comes from the CMB, give you values close to 67. The problem is not like it was in the past, that the difference between the values is not so high. The problem is that the precision that is claimed in these measurements is so high that make these results inconsistent, down to, I mean, at the level of 5 sigma, 7 sigma. So what is the future, or what I think is the future of these things? So far we have covered up to 6, 7, 8 megaparsecs with massive stars. The next generation of extremely large telescope facilities and the instrumentation that they will have will open a window to the far edge of the local universe. So I mean, if the instruments and the telescope deliver what they are promising, it would be possible to do single observations and spectroscopy of single individual stars, massive stars, in galaxies in the Virgo cluster, for example, N100. And this is important because then we will have more galaxies in which supernova type 1a happen, and then we will be able to reduce our statistical uncertainty in the value that we are deriving for the Hubble constant. Nevertheless, I want to stress again, what is very relevant is not that we have an error or whatever. What is important is that we have a completely independent systematic budget. And this is, again, 2 experiments or 3 experiments that are different and telling you exactly the same result. This is my summary. I hope that now you are all convinced that blue supergiants are extremely powerful tools that we can use beyond the limits of the Milky Way for sure and beyond the local group. Stellar spectroscopy, quantitative stellar spectroscopy, can simultaneously tell you things about the stellar properties, the galaxies these stars live on, extinctions, and the distances. And the hope is that future ELT class facilities will allow us to reach even farther in the local universe, reaching the limits of what is there. Now, what I show you is basically a 1-hour summary of work that has been done during nearly 2 decades. And this is not only done for me, by me, this is done with people that I enjoy working with, enjoy spending time and learning with them and learning from them. These are the core of people that I have the pleasure to work with over all these years. Unfortunately, some of them are moving to other things. Life is way more than astrophysics, so this is very important. We will miss them, or I will miss them a lot. But yeah, these are the people that make all these things possible. And I leave you with my last sentence. The blue supergiants are not only bright tracers, they are laboratories that connect stellar physics with cosmology. Thank you very much for your attention.
Thank you very much, Miguel, for this very interesting talk. It's clear that there are many things that can be done with blue supergiants, and there are very interesting future prospects for these studies. So now it's time for questions. If anyone wants to ask or have any curiosity. If not, I have many, but I prefer others to ask. No, then I will start myself. So you have been showing how you derive metallicities and some results related to metallicities, but for sure with these stars you can also derive independent abundances of elements that are also valid for constraining massive star evolution. So could you provide us some additional information of what are the elements you can derive abundances with these B supergiants, and what are the limitations we have in terms of, you see the lines in the spectra, but the model atoms are still not properly developed and will need some improvement there?
Right, so if I can find my own presentation, because I show you something very basic. I apologize beforehand, because this is a figure that I created 25 years ago, I think, or 21 years ago, and I didn't have the time to recreate it, but since you asked for this, I show you. This is, for example, for a A-type supergiant, okay? So what you have here is...
So you're still not sharing?
Oh, okay, thank you, because I was... let me find this thing. Sure. So, okay. Hide this and show this. Now you can see it, right?
Yeah.
Okay, so what you have in the top is a full synthesis of a particular wavelength range where all the elements are included, okay? In this case, is for a typical A-type supergiant. I played the game, again, this is 20 years ago, I played the game to one by one remove elements from the formal solution to see what was the effect. So the first one that I am going to remove is iron. And when you remove iron, you can compare the blue with the red. You see that these are iron lines, okay? Then you do the same. Now you remove titanium, and by comparing the blue and the green, these are titanium lines. You can now do chromium, and then chromium comparing the green and the dark blue, these are your chromium lines. And the rest that is left in this window is barium. So you can play this game for all your spectral windows and your spectral types, and then you will learn what are you really fitting in this kind of a spectra, right? So what the things that you are measuring depends on the spectral type. So for example, for OB supergiants, you have exactly the same lines that you have a high resolution. You miss the weak lines, but the strong lines you still have there. So you have oxygen, you have carbon, you have nitrogen, you will have silicon, you have magnesium. These are the things that you can, in theory, you can measure, and in practice, you can measure individually in a OB supergiant. In a VA supergiant, you have silicon, you can measure iron, titanium, chromium, you can measure for sure magnesium. If you push it, and if you have the right wavelength range, you could measure oxygen, and you could measure nitrogen. This comes from neutral oxygen lines and neutral nitrogen lines. Carbon would be very difficult, because at least in the optical, neutral carbon has relatively weak lines. So these are the kinds of things that you can do. If you are interested in stellar evolution, then the low resolution spectra of OB-type stars will still give you carbon, nitrogen, oxygen, and helium. If you are interested in metallicity measurements, what is more relevant, for example, for things related to the distance, is measuring metallicities, because these affect the physics of the objects, then you are better set with B and A-type supergiants, because they are full of this kind of lines.
Okay, thank you.
Answer your question?
Yep.
Good.
So anyone want to ask Miguel? Paco?
Hi, Miguel.
Hi, Paco.
Really nice talk. I was missing Nadine in your... yeah, so my question goes related to what you just said before. I mean, if you look for the BA, you miss oxygen, nitrogen, yet you were comparing what you call metallicity. So I guess this set you were saying sometimes is related to oxygen, and some other times is related to iron. So I guess you have to rely on a precise relation between alpha elements and iron when you show your plots. Is that correct?
I think you are thinking, let me show again, on the NGC 300 plot, right?
Yeah.
So You are correct. So what is done here, for example, is that for the H2 regions, where, as you are right, in the H2 regions, what you measure is oxygen, and this is what people doing ionized gas use as a proxy for metallicity. Here, the oxygen of the H2 region is converted to a metallicity or a reference scale using the oxygen in Orion in M42. Okay, so we don't mix apples and pears. The reference for each kind of object is the same kind of object. For the H2 regions, oxygen from the local H2 region. For the stars, is the same measurements from our galactic stars, and so on and so forth. So let me, to make the point that Paco is trying to make, I think, and I think this is very important to understand, is this point, here. This is a figure that comes from an old review from Williams in 1997. When you have a stellar system, the stellar system will evolve in time, with generations of stars polluting the material and then evolving. So the relation that is in a stellar system between the alpha to iron ratio and the iron will change with time, and because of the initial mass function and because of the star formation rate. And this is related to the different time scales of evolution. Massive stars evolve faster, so they die faster, so they pollute the medium with the elements that they produce, which is basically alpha elements: oxygen, sulfur, calcium, titanium, things like that. You have to wait until the system will wait. The system has to wait until the first low mass stars will explode as supernova type 1 to enrich the medium significantly in iron. So this is why this alpha to iron ratio is not universal, as many people assume. It depends on the galaxy. It should vary from galaxy to galaxy because each galaxy has an independent evolution history. So we see that in the galaxies in the local group that we have been able to measure iron from one kind of objects and oxygen from another kind of objects, stellar objects, even in the case of high-resolution observations of BA-type supergiants, you can measure both in high resolution. You can measure your oxygen, and you can use silicon or magnesium, and you can measure your iron. And there are some galaxies, some dwarf galaxies in the local group, and that have evolved in a particular different way because they are isolated or things like that, where this ratio is clearly non-solar. So this is an assumption that is sometimes made, that the solar ratio applies everywhere. This is not true. Does this answer your question or help your question?
I think so.
Thank you, Paco.
Thanks, Miguel.
Okay, now we go to Joe.
Hi, Miguel. Thanks a lot for this fantastic talk. I have also a question regarding iron, because you told us here that you have also analyzed iron lines, at least in the optical. So there are two related questions. The first one is, where do you have your model atoms from? Are they own ones, or have they been taken from other databases? That's number one. But the most important question in this respect is the following. You might know, or you surely know, that when you look at least for hot O stars and so on in the ultraviolet, where you have the iron lines, that there is a certain discrepancy between the lines which are predicted and which are observed. They are so-called non-observed lines. And my question would be then, have you ever seen something similar in the optical? And if you don't see it, what does this mean? I mean, when you see some problems in the ultraviolet, I would assume that there are also problems in the optical. So these are my two related questions.
Okay, so as you know, I am very lucky, and I work with Norbert Pritzvilla, that works with, I forgot now, the Butler in Germany. So our atomic data come essentially from that, from what Norbert has done. This is iron 2 lines, and you can see this is, for example, in the spectrum of an A supergiant observed with X shooter in IC 1613. In principle, I've never, maybe you can say, okay, your lines here, whether these are really lines or your model is predicting lines, but it's difficult to say because in this case, the signal to noise is not that great, right? So I wouldn't know, but I think the problem is way more, for sure, more evident in the ultraviolet than in the optical lines. Why? I have no idea.
Okay. So how many levels do you have in typical levels per
I
ion? Roughly.
I will have to go to the model and tell you that.
Yeah, roughly. Is it on the orders of a couple of hundreds? Is it thousands or whatever?
No, I don't think that is thousands. It can be close to hundreds, yeah, but not thousands.
Thank you. Okay, so this is something we have to look into because this is something which always has me puzzled because when there is something rotten in the ultraviolet, this usually refers to the lower levels and the higher levels which are displayed in the optical are coupled to the lower levels. So
may I jump in, Joe?
Okay, maybe you know the answer.
No, I don't know the answer, but if you remember when we started doing these genetic algorithm codes and blah, 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 and all this fitting, if you use the CMF-GEM models and you use the also unobserved lines, there were models produced by Rohit a long time ago that showed a lot of iron 4 and iron 4 lines in the optical that were not observed. So my suspicion is that people have classically worked with the lens they see, and in the optical world Coles does. So they've been chasing every single dip they've seen there, and that's why the information about all the iron 2 transitions is so complete, and that's how the iron 2 atom it has so many lines, and yet you see the NIST or the iron project or the other line list, and still you find a lot of differences in the oscillator strengths. But just to summarize, these iron 4 lines were produced as non-observed by the CMF-GEM models if you look into detail. In the optical, they are seen. And yet they are not observed. The same as in the UV.
Okay, thank you, Paco, for the extra information. It's clear that this is something that requires some more studies. Any other question here by the audience? So then I want to ask you, because I want you to go back to this metallicity mass relationship that for me is amazing. I remember the first time I saw that in a MIAP workshop that Kudryski showed. And in addition to all what is inside, because as you told me, this requires a lot of work to end up with this figure. So what is this figure telling us about evolution of the universe? Is just a normal consequence of more massive galaxies, more stars, more metallicity, or is this telling us anything else in a cosmological scale?
Galaxies are very complex systems, right? So this relationship that looks quite simple is set by a number of things. The evolution of the galaxy is the galaxies are not isolated. There is still inflow of gas and things like that. They are forming more stars and so on and so forth. So when if you can compare this relation that you get locally, so now in the universe, with the same relationship at different redshift, so in the past of the universe, you can see how this relation is evolving, right? So to the point that if you go far enough back in time, the relationship should be flattening, okay? Because what you see now is what has happened. Our M31, M33, the Milky Way have had more massive galaxies. They evolve faster. This is what makes that the relation makes this, right? So per se, this galaxy established the 0 point, let's say the local value. And then what you need to do is people that do high redshift galaxies can compare what they get with this thing. And then of course, any simulation that you make of the universe should be or able to predict match how this relation is changing with redshift.
Okay, so related to the second question I wanted to ask you, now you say at the very end of your talk that now we are going to have ELT, and there will be the volume that we are going to be able to investigate just with this method would be larger. So I thought that it was going to just populate the same relation, but then I understand that there will be, we will be able to, not yet. So it has to be.
It's still with, so we cannot, in distance, stars, single stars cannot compete with ionized gas or anything like that. In an H2 region, in ionized gas, you have a lot of energy that has been reprocessed by the gas and emitted in one line. So the intensities of those lines are tremendous compared with our spectra, so you can reach very far away. We cannot compete with that. We cannot do that with our stars. We can offer precision. We can offer complementing the results, because with ionized gas, they cannot measure iron, they cannot measure other species, right? But the window that is opening, the ELT will open, is still is what is called, or what I would call, the edge of the nearby universe. We are still at a distant modulus that is not even 30, right? 30 magnitudes. So we are still, in terms of cosmology, we are still within we are not reaching the Hubble flow, where galaxies are, the movement of galaxies is dominated by the expansion of the universe, not by local movements, right? So no, we are not. What we can do is populate this relation with more massive galaxies. There are some massive galaxies in the Virgo cluster, massive spirals, but that's it. We cannot see how the relation is evolving.
Okay, so we are extending the range in mass, in mass, and also we are making a better sampling of the relation with many more, but not yet
for this kind of things, yes.
Okay, thank you.
Yep.
So last opportunity to ask questions to Miguel. If not, as I always say, if you are watching this in the future and you are still interested and you have questions, I'm sure Miguel will be happy to answer you by mail if you contact him. So thank you very much, Miguel, for this interesting talk, and thank you everybody for joining us today, and see you soon.
Thanks, Miguel.
Yep.